You know that feeling, right? Staring at a massive spreadsheet or just a total jumble of disconnected information? It's a complete nightmare. It's chaotic, confusing, and pretty much impossible to work with. But what if I told you there's a way to bring order to all that chaos before you even get started? Right, let's get into it. Think about it. An architect would never ever try to build a skyscraper without a detailed plan, right? Well, it's the exact same idea in the world of data. You never build a database without a blueprint. And that blueprint, it's called an entity relationship diagram. So what is this thing exactly? An ER diagram is basically a visual map. It's the professional's tool for showing you all the pieces of your data, how they relate to each other, and the rules that hold them together, all in one clear graphical picture. It's how we turn that data nightmare into a beautifully structured system.
So, here's our game plan for this explainer. We're going to walk through this blueprint idea step by step. First, we'll look at the core building blocks. Then we'll add in all the little details. After that, we'll see how all the pieces actually connect. And finally, the really important part, we'll cover the rules for turning this plan into a real working database. Every blueprint has to start with the big stuff, right? The walls, the floors, the main rooms. Well, in an ER diagram, our main structures are called entities.
So an entity is really just a thing we want to store information about. It could be a person, a car, or a company, stuff that physically exists. Or it could be something conceptual, like a university course, a job, or a school. And when you group a bunch of the same type of entity together, like all the students in a school, we call that an entity set. Simple as that.
Now, not all entities are created equal. You've got your strong entities. Think of a building. It can exist all on its own, and you can uniquely identify it, say, by its street address. But then you have a weak entity, like an apartment. An apartment can't just exist on its own in thin air. It needs a building, and its door number only makes sense inside that specific building.
And this table here really breaks down the key differences for us. Strong entities, they've got their own primary key, that unique identifier like a building address, and you'll see them drawn with a single rectangle. Weak entities, on the other hand, get a double rectangle. They borrow their identity from a strong one, and they're always in total participation, which just means every single apartment must belong to a building, no exceptions. Okay, so we've got our main structures. Now it's time to add the details. Just like a room in a blueprint needs dimensions and features, our entities need descriptive properties, and we call those attributes. So yeah, attributes are just the descriptive details. If we have a student entity, the attributes could be their name, their age, or their student ID number. Each attribute holds one specific piece of information that helps us describe and define that entity.
All right, let's run through the different types really quick. First up, we have simple attributes. These are atomic, which is a fancy way of saying they can't be broken down any further. Think of a student's age or their roll number. It's just one single piece of data. That's it.
Next, we have composite attributes. And these are the opposite. They're made up of a bunch of smaller, simple attributes. A person's name is a perfect example. You can break it down into first name and last name. This gives our blueprint way more granular detail.
Then there are multi-valued attributes. These are for when an entity can have more than one value for the same property. I mean, think about it. A person might have 2 phone numbers or 3 different email addresses, right? This attribute type lets us capture all that real-world complexity.
And finally, we've got derived attributes. Now, this one's pretty clever. It's a way to be more efficient. An attribute like age doesn't actually need to be stored in the database at all. We can just calculate it whenever we need it, using the date of birth. This keeps our database clean and stops us from storing redundant, unnecessary data.
Okay, this is where it all starts coming together. We have our building blocks, the entities, and we have their details, the attributes. Now it's time to show how they all fit together. A blueprint isn't just a list of rooms, right? It's a plan that shows the doors and hallways connecting them. This is where relationships come in.
A relationship is just an association between our entities. So, a student entity connects to a course entity through the action enrolled in. A relationship is basically the verb that links our nouns together, explaining how they interact with each other. But these connections aren't random. They have rules, and we call these rules cardinality. It's just a word that defines how many entities can be connected. For example, you might have a many-to-one relationship. Many employee entities can be part of one department. See? Many employees, one department. That's cardinality.
And there's one more rule: participation. This tells us if a connection is mandatory or optional. Total participation, and you'll see this shown with a double line, means every entity has to be in that relationship. For example, every student must be enrolled in at least one course. But partial participation, a single line, means it's optional. A course might exist with 0 students enrolled in it yet.
All right, we've designed our blueprints, we've got our entities, our attributes, and all the relationships that connect them. Now for the payoff. This is where we turn this detailed plan into an actual, functional database structure.
You know, the creation process itself is super logical. You just identify your things, your entities, then you figure out how they connect, the relationships. You define the rules of those connections, the cardinality. You list out their properties, the attributes, and then you draw the diagram. It's a really systematic way to model your data.
So why do we do all this? What's the point? Here it is, the key takeaway. The entire purpose of making an ER diagram is to convert it into tables. These tables are the basic structure used by what we call a Relational Database Management System, or RDBMS. You know, powerful software like MySQL or Oracle that actually stores and manages all the data. The diagram is the plan, the tables are the finished building.
So how does that conversion actually happen? How do we get from the drawing to the real thing? Well, there's a clear set of rules for translating every single part of our blueprint into database tables. Let's break down the specs.
These are really the core rules you absolutely need to know. A many-to-many relationship, that will always require 3 tables. A one-to-many relationship only needs 2, because the many side of the relationship just absorbs the information. And a one-to-one also needs 2 tables. Seriously, getting these rules down is the key of practical database design.
And what about our weak entities? Remember the apartment in the building? Well, it has its own special rule. And the magic number you need to remember is right here, 2. A weak entity set will always result in a minimum of 2 tables. You'll have one table for the strong entity it depends on, and a second table that combines the weak entity with its relationship. It just can't stand alone.
So there you have it. You now have the architect's tools. You understand the entities, the attributes, the relationships, and most importantly, the critical rules for turning that plan into reality. So the final challenge is putting it all together. If you were handed a complex blueprint like this one, with strong entities, weak entities, and all sorts of relationships, could you figure it out? Based on everything we've covered, how many tables are needed here?